So we have an electric field E, right, which is r over r squared times some constant, and we need to find the divergence and the curl of this E field. Now note that this is not the electric field from a point charge, because that would give you r hat over r squared. R vector over r squared is the same thing as r hat over r cube, right? So that's kind of the idea. So we need the divergence. So remember the divergence in spherical coordinates here. We have to use the divergence in spherical coordinates. Now, this is in the back cover of your book, because the electric field is given in cylindrical coordinates. So the divergence of E is equal to, now there's the theta component and the phi component, which go to 0, so we don't need those. But the other ones is 1 over r squared d over dr of r squared er, with er being the radial component of the electric field, which in this case the radial component of the electric field would be, because r vector is basically the r magnitude of r times r hat, right, divided by r squared, and we could cross an r here, so this would give us c over r hat, sorry, r hat, because what's r hat? The vector divided by the magnitude of the vector. So one of those r's cancels out. So my point is er is what multiplies r hat, c over r, with r being magnitude here. And so the divergence becomes 1 over r squared d over dr, r squared times c over magnitude of r, and 1 r here cancels out, yeah, and we get 1 over r squared, derivative of cr is just c, so then we get c over r squared, right? So now, so this would be the answer. Yeah, now we have to test this using the divergence theorem, right? And the divergence theorem says that the integral of EDA has to equal the divergence of the integral of the divergence d tau on V, and this is on surface S. Well, we'll figure out each one separately. So this is the divergence theorem here. for this electric field. This is how you turn a surface integral into a volume integral, or backwards, right? Yeah, so we could test it. This is on S, any surface. So if this is on the surface of the sphere, at the surface of the sphere, we know that R has to equal capital R, right? So this becomes, what's E? C over R, right? We'll do a double integral. Actually, let's do let's do this. And then we know that dA in spherical coordinates is R squared sine theta, and R is constant, so we don't have to worry about it. Oh, actually, let me put the vector here. So this is in the R direction, right? Because that's what E is. It's in the R direction, R hat, dotted with R squared sine theta d theta d phi. And this is the area vector is perpendicular to the surface, so it has to be also in the radial direction. And as you can see, when I do R dot R, I just get a magnitude, right? And so this becomes R squared and R, so I'm left with CR, right? R dot R is 1, and I have sine theta d theta from 0 to pi, and d phi from 0 to 2 pi. And the sine theta from 0 to pi would give me 2, right? So this integral here is 2, this integral here is 2 pi, and so I would get 4 pi CR. Okay, so this is the left hand side. Let's do the right hand side. So the right hand side is divergence of E d tau. Okay, on V. Okay, we already found the divergence. It's C over R squared times R squared. So d tau would be R squared sine theta dr d theta d phi on V. So R squared can cancel out, and so now I have C dr from 0 to R, capital R, and I have sine theta, just like above, d theta from 0 to pi, and d phi from 0 to 2 pi. So this here will get me an R, this here will be 2, and this here will be 2 pi. So clearly I get 4, and there's a C here, so 4 pi CR. So this is exactly the same as this. Therefore the divergence theorem checks. So now I could say that the divergence of E d tau on V is indeed equal to E dot dA, right, on surface S. So we proved that the divergence theorem works because we got the same answer. Now, is there a delta function at the origin here? No. No delta function involved here. Clearly. Okay. So what's left here is to find the curl, and that's in spherical coordinates. Again, you don't have a theta and a phi, so there'll be one component for the curl, which is the r component. So the curl of E will be 1 over r sine theta, right? Well, not, I mean, there's certain component parts that will vanish, yeah? All the d thetas will go away because the angle is not changing, so let me erase that. So d over d theta sine theta v phi, that would go away. There's no v phi is 0, v theta is 0. We only have from the second component in the theta, we have 1 over sine theta. Oh, even this one vanishes because phi is not changing, so dvr over d phi is 0, right? And the second component for the theta is also 0 because v phi is 0 and v theta is 0. So the phi component, both terms also vanish because v theta is 0 and vr is not changing with d theta, so the second component of the theta will be 0. So that means the curl of E would have to be 0, according to the definition of the curl in spherical coordinates. So this is our curl in spherical coordinates for an A in general. This is like for any A, with A here being the electric field. I'm not sure if they're counting the theta here and the phi backwards, because the math people use theta and phi interchangeably, but nonetheless, we know that there's no change in theta, so this goes away. There's no change in phi, so this goes away. So the whole r component is 0. Also, the r component is not changing with phi, so this is 0. There's no phi component, this is 0. So d over dr of that is 0. A theta is 0, so this goes away. And the AR component is not changing with theta, so this goes to 0. So all of them are 0. So that's why the curl is 0. And we know that the electric field is curlless anyways, so there wouldn't be a curl. Okay, now it's saying what are the units of C, right? Well, that should be fairly evident from the relationship, because we know that E, so this is part B, is equal to C r over r squared, right? Okay, so that means C, let's use dimensions here, is E okay, so C is ER squared over vector R. Well, we know that the electric field is in this is force per charge, right? So newtons over meters, and R squared is in meter squared, and R is in meter. So these two guys go away, and C has to be in newtons, yeah? So which is so C has to be in newtons.
How come you have R squared?
So it's a force,
How come R squared is on top?
If you solve for c, wouldn't r squared be on top? Cross multiply, huh?
Right, yeah.
And so, having said that, c turns out to be in newtons. Yeah, sorry, I meant to write newtons per coulomb, and for some reason I wrote newtons per meter. Never mind. I was wondering that this is not possible to have c in. This is coulombs, meter square over meters, so c has to be in newton meter over coulomb.
Wouldn't that be potential?
Yes. Newton meter per coulomb, because newton over coulomb is the electric field, right? So that would be E dot meters. Yes, this would be the potential, correct? So this is in volts. Now, is this reasonable to get something like this? Well, we know in general that E equal minus let's see, we know in general yeah, it's the gradient, or we could say that V is equal E dot dl, right? Yeah, or we could say that E is equal the negative, there's a minus sign here, this is from the reference to whatever point we are interested in R. Okay, so it's minus the gradient of V, right? So if you replace C with V, then we have E equals C, or in this case, since it's a potential, let's just call it V prime to see if it's possible, R over R squared. Right? Which is, that means and this has to equal to the gradient of V prime. Right? So that means V prime, this is gonna be, we said that if we make this unit vector R, okay, this becomes over R, right? Because R is R vector over the magnitude. And this has to equal to the minus the gradient of V prime. Okay, well, let's see if we could solve for this. What's the gradient of V prime? The gradient of V prime, well, only the R component survives here. And we go back to spherical coordinates, and we use the same component we used. Well, actually, no, we didn't use that yet here on this question, but the gradient in spherical coordinates would be d over dr of V. So this is minus d over dr of V prime. Okay. and that is in the r direction. Okay. So that means this has to equal this. So that means v prime over r has to equal minus d over dr v prime. This is a differential equation. We can integrate that. So this becomes dv prime, right, over dr. This is like saying d over dx of y equal y prime over x, right? So we could solve this by saying that dv prime over v prime, right, is equal to minus dr over r. With dv prime over v prime, yeah, and I took the dr to the left, so d over dr, and if I integrate both sides I get ln v prime equal minus, why is this quitting on me, equal minus ln r plus c. So we get v prime, if you solve this exponentially, will be it will be c e to the minus r. So we would have to have a potential that behaves as such, exponentially decaying, to get an electric field in that manner. Now the only thing here that I didn't do, which I'm thinking whether I should do it or not, because I don't consider this a main idea for this chapter to go further on this, considering that you have an exam tomorrow, is whether I should pursue the theta and the phi components of the potential of the gradient and set them equal 0 and solve for the other constant in this equation to see whether it's even possible to get something like this. Okay. Right. But just the fact that V could be a potential tells me that this kind of electric field may not be possible. The reason being is because if C has the components of a potential and the electric field is technically the integral of or the gradient, right? So it should simply put is if you multiply the right hand side, so this is over r squared, right? So technically the electric field here magnitude is just C over r. Okay, that's what we're basically saying. Okay, C over r. Now if you multiply the r on the right hand side, you get C to equal ER, magnitude. So, and it's the integral of EDL, which would make sense because if DL is R, then you would get C to be the correct outcome. Nonetheless, the main ideas of the question remain on how to find the divergence in spherical coordinates, the curl, and how to test the divergence theorem and figure out the units.